So we're going to talk about network covalent structures. And so the objectives are to be able to describe, compare the structure and the bonding in the allotropes of carbon. There are 4 allotropes. Your book may just say 3, but there are 4. These 4 that we're going to look at are diamond, graphite, graphene, and something called a C60 fullerate. And then after we talk all about carbon, we're going to talk about the structure of and the bonding in both silicon and silicon dioxide. You're going to need to know, probably memorize, some things about these structures and how they're related to the properties of these materials. Okay, so just a little bit of background before we get started is, 1, there are things that are known as giant molecular structures, also known as giant covalent structures. And these are crystalline in nature. Okay, so they kind of look like ionic lattices, but they don't have ions at those points. They actually have molecules or atoms in those places. All right, actually atoms. They have atoms at the lattice points. And they link together with covalent bonds. All right, and a crystal is a single molecule with a regular repeating pattern of those covalent bonds. This might be a little small, but types of bonding in crystalline solids, and we've talked about, I think we've talked about all these. We have molecular, all right, where you have atoms or molecules. These are where you have the intermolecular forces between the particles. We find these, and these are the normal covalent structures that we talk about as far as substances. You're going to find that these are fairly soft, low to moderately high melting points, poor thermal and electrical conductivity. Things like argon, methane, sucrose, dry ice, all of these fall into what we call a molecular solid. And again, we've talked about these for a long time. All right. The second thing, and this might be kind of new, is talking about covalent network. All right, these are definitely atoms connected in a network of covalent bonds. So the things that hold these atoms together are covalent bonds. It's just that they go on repeating. All right. So instead of intermolecular forces, we actually have covalent bonds. These substances tend to be very hard, very high melting points, and they differ in their thermal and electrical conductivity. Examples of these are diamond, quartz, which is silicon dioxide. All right, so these are 2 of the structures or compounds that we'll be talking about. Another type of bonding in a crystalline structure is ionic. We've talked a fair amount of that. Positive, negative ions. These are held together by electrostatic attractions, that attraction between negative and positive charges, or ions. Ionic compounds tend to be hard and brittle. They have high melting points, and they are poor thermal and electrical conductors in their solid state. Right, we'll find that this changes the electrical conductivity if it's in solution. Okay, we know these things as salts, things like sodium chloride, calcium nitrate. And then metallic bonding, we've talked about metallic in the last chapter. Particles of this unit are atoms, all right? Metallic bonds, remember, these are really cations, positively charged particles with mobile electrons. A sea of electrons is the model. Remember to say that it is an electrostatic attraction between that cation in the lattice structure and the mobile electrons. Metals tend to be anywhere from soft to very hard. They have low to very high melting points. They are excellent thermal and electrical conduction, electrical conductors, mainly because of those mobile electrons. Metals are malleable and ductile, and we'll get into those definitions. All right, and what are metals? Well, they're all of the metallic elements. For example, copper, iron, aluminum, platinum, all metals. All right, let's switch gears and talk specifically about, oh dear. Oh, I didn't want it to do that. Oh, all right. Hang in there with me. All right, so let's define what is known as an allotrope. So what is an allotrope? An allotrope are really just different forms of an element in the same physical state. There's different bonding within the structures, and because I have different bonding, I have a different physical properties associated with these different allotropes. As mentioned earlier, carbon has 4 that we'll be looking at: diamond, graphite, fullerene, and graphene. Graphite, this is the stuff that you write with your pencil. Diamond, shiny things, very pretty. So let's look specifically at graphite. This is a picture of graphite. Okay, you can see that it consists of a 6-ringed member here, all right, with each of the carbons sp2 hybridized. Okay. They are covalently bonded to 3 other carbon atoms if you look at just one layer, and they form parallel layers. Okay, parallel layers of these hexagonal sp2 hybridized covalently bonded carbon atoms. These different layers are held together by these van der Waals forces, okay, between those carbon atoms. Remember, these are fairly weak intermolecular forces, and what that allows is movement of these layers over one another. And that's actually what you get when you use your pencil, is you're sliding these layers of graphite off of that graphite solid part in the middle of your pencil. Density is 2.26 grams per centimeters cubed. Because these carbons are only sp2 hybridized, okay, there is a non-bonded delocalized electron for every 1 atom in this graphite structure. Because I have a delocalized electron that's able to move, graphite does conduct electricity, and it's important to know that. It's important to know that there's hexagons in parallel layers. Because it's sp2 hybridized, I have a bond angle of 120. It's important to know that these carbons in that hexagon are covalently bonded. It's important to know that the layers are held together with relatively weak van der Waals forces, IMF forces. Okay, and they can slide over each other. Because I have that sp2 hybridization, I have 1 delocalized electron, which means it's highly conductive electrically. It is not a very good heat conductor. It has a very high melting point, and it says it's the most stable allotrope. Okay. If you look at the lead in your pencil, it's not very shiny, and it's a gray solid. Okay, let's look at diamond. Pretty diamonds. Here is the structure. If you look at the crystalline structure, so diamond. So we see that there are some differences between diamond and graphite. In diamond, each of the carbon atoms is sp3 hybridized. So this means it is covalently bonded to 4 other carbon atoms in a tetrahedral repeating pattern. Because it's tetrahedral, you should know it has a bond angle of 109.5. So every carbon is attached to 4 other carbons. It is the hardest known natural substance. Its density is 3.51 grams per centimeter cubed. I don't think it's important to memorize the density of it. Because these carbon atoms are sp3 hybridized, meaning they each make 4 covalent bonds in this structure, all of the electrons are bonded. So there are no free moving electrons, so it does not conduct electricity. Diamond does conduct heat better than metals. It has a very high melting point and it is brittle, meaning if you were to smash it with a hammer, I guess hard enough because it is a very hard substance, it will shatter. It is a lustrous crystal. It's used in jewelry and it's also used in tools, particularly like saws and drills. Okay, so let's take a minute and look at kind of the second to last allotrope, kind of related to the last one as well. And we're going to specifically talk about something called a fullerene, which is a C60. There are 60 carbons in this structure. All right. Each of the carbon atoms is sp2 hybridized, and it is important to know the hybridization between the different things of graphite, diamonds, and this fullerene C60, also known as a buckyball. All right. Each of those carbon atoms is covalently bonded in a sphere of 60 carbon atoms with 12 pentagons and 20 hexagons. All right. So you can see here is a pentagon, and right next to it is a hexagon, right? And they're bonded covalently to 3 other carbons put together to make a sphere. All right, so the structure is a closed spherical cage in which each carbon atom bonded to 3 others. Relatively low density compared to the graphite and the diamond. It has a density of 1.726 grams per centimeter cubed. It easily accepts electrons to form negative ions. It's known as a semiconductor at normal temperature and pressure, okay, because it has some electron mobility. It has a very low heat conductivity, so it doesn't conduct heat very well, and it has a low melting point. If you have a bunch of this, enough to make a solid sample you can hold, you would see that it is a yellow crystalline solid, and it is soluble in benzene. Benzene is a non-polar substance. Okay, and this gives you an idea. Here is the buckyball. These are things known as nanotubes, and we'll take a look at those. All right, so again, the hybridization is important. That it makes a sphere made up of 12 pentagons, 20 hexagons is important. Okay, just wanted to show you a little slide, I think, that explains a little bit of graphite, graphene, and fullerenes a little bit better. Here's your graphite consisting of those layers of hexagons held together by those van der Waals intermolecular forces. If you were to take a single layer of this graphite, that's when you would have something called graphene. And we'll talk about that next. Perhaps I should we'll talk about that next, all right? But it is a single sheet of these hexagons of graphite. If you were to roll that graphene, that single layer up, you would have what's called a nanotube. If you were able to close, and you can actually close these tubes to make it more of a capsule, okay, you would have what's known as a fullerene. The fullerene that we talk about is that C60 fullerene, but you can also close up these nanotubes. All right, I don't think you need to know that. I think that's part of the one of the special topics. All right, so kind of this all hopefully makes sense. All right, but this is the buckyball with the pentagons and hexagons making that spherical cage. So let's go and learn a little bit more about graphene. Okay. Here we got that single sheet of the hexagons. So hopefully you can see each carbon is bonded to 3 other carbons. It has, happened to my pen, it is an sp2 hybridized, covalently bonded to 3 other carbons. Because it's sp2, it has 120 bond angle. This is a single, like 2-dimensional single layer, okay, described as a honeycomb or a chicken wire structure. Density is pretty light at 1.5 grams per centimeter cubed. This graphene, because that carbon is only bonded to 3 other carbons, has 1 non-bonded delocalized electron per atom. So graphene conducts electricity because those unbonded delocalized electrons can move throughout the structure. This is an excellent heat conductor, better than diamond. It has a very high melting point. It is the thinnest material to exist, and it is stronger than steel, which is just hard to wrap your head around, that it is just a single layer like this, but it is stronger than steel. It is almost completely transparent because it really is only 1 atom thick. It is used in touchscreens and high-performance electronics. All right, so that's graphene. Let's talk about silicon and then silicon dioxide. Silicon is the structures that you see here and here. Okay, all the same atom. Silicon is a group 4 element. It's got 4 valence electrons, very similar to carbon. In its elemental state, each silicon atom covalently bonded to 4 others in a tetrahedral arrangement. We get a giant lattice structure, much like diamond. All right, and that's what you see here. You get your silicon, 4 bonds, and it just keeps going. Okay. Here I put silicon dioxide on the same page. It really should be on the next slide. Let's go to the next slide and see what we can say about silicon dioxide. We may come back to look at the pictures. Silicon dioxide is known as silica or quartz. And again, we're looking at giant covalent structures, all with covalent bonds in between. Silicon dioxide is also a tetrahedral structure, but the bonds are between silicon and oxygen. Each silicon atom, which is here, is bonded to 4 oxygen atoms. And each oxygen is bonded to 2 silicon. So here you have an oxygen bonded to a silicon atom. The formula SiO2 is the ratio of atoms within the giant molecule. So this is very similar to an ionic formula unit. The structure of silicon dioxide is strong. It is insoluble in water. There are no free electrons, so it does not conduct electricity or heat, and it has a very high melting point. Okay. These are all properties of glass and sand, which is what silicon dioxide makes up. All right, and these are different forms of a common group called silica that both of these fall into. All right, if we go back, this is a picture of quartz, and then this is your silicon dioxide structure again. It may be helpful to make a chart similar to this. These are the 4 allotropes of carbon, listing the different properties in a table structure, and maybe getting a picture might help for studying. That completes this discussion of giant covalent compounds.